Hi, my name is Robin Vertier, and I'm a research scientist here at the Information Trust Institute working for the TCIPG Center. With Ahmed Fawaz, I will present our work on intrusion detection and automated response for advanced metering infrastructure. This work is a team effort involving also David Kochhauke, Eric Heine, Jeremy Jones, Edmund Rogers, Bill Sanders, and Tim Yardley. So, large advanced metering infrastructure are being deployed all over the country, and those involve a large number of smart meters. Those meters have computer-like capabilities and could be targets of interest for malicious activity. So we need a resilient solution to be able to detect malicious behavior and to be able to automatically respond to it. Over the past 2 years at the TCIPG Center, we've been working on a unique IDS system called a specification-based IDS. It's unique because it's not relying on a database of known attacks like a signature-based IDS like Snort will do. It's really focusing on leveraging the knowledge about protocol, about network and expected behavior to be able to detect malicious activity. So we built a prototype, and now we have deployed this prototype in embedded computers called Beagle boards. And the goal of the demo today is to show you how those sensors can help us getting situational awareness over AMI and be able to detect attacks, and also how we integrate these sensor capabilities with our response and recovery engine. So we showed a demo last year where we focused really on the detection part and explaining how we could use mathematical tool to prove the coverage of our checkers. Since last year, we've made some major research and technology achievements. And the first one has been to really work on the flexibility and the resiliency of the sensor. So now it's really easy to deploy on any type of platform, a large server at the head end or a small embedded sensor in the field. Sensors are autonomous, and they are self-configuring and self-reporting. And they use a standard logging format so that you can easily deploy them with your existing security infrastructure. They can send events to security event managers. Another milestone has been to initiate technology transfer activities. So we are collaborating with Itron, who has provided a meter test bed. So now we have 23 meters and cell relays and collection engine in the lab. And last year we've been showing the IDS using virtual meter run by software. This year we have real hardware meter, and those are communicating right now. They're being deployed in the building and monitored by the sensor. Another tech transfer activity has been to start a collaboration with First Energy, where we are now deploying our application in one of their test AMI with 40,000 meters. And this helps to understand the scalability issue and to make sure the sensor is working well. Finally, a third milestone has been to integrate this IDS system with our response and recovery engine. And the goal of the demo today is really to show you how this automated response works and how it can help a security administrator get high-level and meaningful information about how to respond to attacks. So, before doing the demo, we'll first motivate the goal of automated response, and for this, Ahmed will present.
So, as Robin said, we're expecting the sizes of AMIs to be huge. And with this big size of an AMI, there will be a lot of alerts coming into the security event manager, and thus it would be a hard job for the administrator to manage the alerts. And with the complexity of attacks increasing, it's really infeasible for an administrator to automatically handle the attacks, and thus we're proposing using automatic responses and recovery to manage the security of an AMI network. For this purpose, we started by proposing a taxonomy of responses for AMI. And basically the goal is to mimic the way an administrator would respond to an attack. First kind of action would be a learning action that could be either passive or active. A passive action would basically try to learn an attack without actually injecting packets, and there's also active attacks. In terms of modifying attacks, the goal of these is to block an attack and then recover from it. The way RRE works is the following. You get all sorts of IDS alerts from the security manager, and you map them to our attack response tree, and these are then sent to a decision process which optimizes the cost and selects the optimal response. Our cost model, on the other hand, tries to compute the optimal, the actual cost of a response for the utility, and basically this is our conversion function, and then we got the cost on impact, and we add all of the other administrative costs to our response.
All right, thanks, Hamed. So now for the demo part, what we have on the visualization displays, we have the situational awareness console, which shows all the activity between meters and the collection engine. Each yellow circle is a meter, and then the blue ones are client, so collection engine or cell relays. Every time there is a connection between the meter and the cell relays, we'll have a green line being shown. And in case the flow, the communication flow analyzed by our sensor doesn't respect the security policy, an alert will be shown on the screen. Of course, no one can look at this display for very large networks, so that's why we also have traditional security manager, which just log alerts sent by the sensor. On top of it, we have our response and recovery engine, so it's showing an attack tree, an attack response tree, for the specific case of disconnecting a meter and trying to make the service unavailable. So the difference between those two is that the top one shows high-level information on which a security administrator can understand exactly what the security state of the system is. The bottom one is just showing a stack of alerts when they arrive. And so we'll see how those two react when we do the demo. For the demo itself, our testbed architecture is made of 3 neighborhood area network. We have one on this floor, one on the floor up, and one on the floor down. We have 3 cell relays. One of them is deployed in the corner over there. And then we have 23 meters. I think we have about 12 deployed on this floor, and then 3 and 5 deployed on other floors. The attack scenario will consist of having a malicious insider connecting to the collection engine and then sending a remote disconnect to 1 meter. And so Eric will play the attacker, and so he will now connect to the collection engine and try to issue the remote disconnect. So we see that this remote disconnect violated the policy. It wasn't expected that this meter receive a disconnect at that time. So an alert is being displayed, and immediately we see on the security manager that the alerts are piling up, and our response and recovery engine update the tree to show the new security state. So now we have a service unavailable for 1 meter, so different responses are being analyzed, the cost is being computed for each of them, and the response with the optimal cost for the security administrator is being shown in green. So now 2 options. Either we configure RRE to automatically issue the response, or we just use it as a guide to help an administrator choosing the best response. In our case, we have David here playing the administrator who has received the alert, and we will now accept this decision and issue the OK command to get the response. The response has been sent back, so 2 types of responses. One has been to remotely connect the meter that has been disconnected, so service is restored. And the other one has been to block access to the collection engine for the specific IP that was triggering the attack. The attack tree showed us that the system is back in a secure state. And now if we have the attacker trying again the attack, the fact that it's blocked prevent any more remote disconnect from being sent to the meter. So our system is safe again. So in conclusion, we have shown the capabilities of a sensor that we call the AMI laser sensor. It's a whitelisting technology. It helps to really enforce a security policy on a large network where all the nodes are expected to behave the same way. The major milestone has been to work on the flexibility of deployment of the sensor, and also to initiate some tech transfer activity with industry partners, and finally to integrate our detector with an automated response engine. Next step in the research include to continue our tech transfer activity, and also to work on finding optimal sensor placement in the field, and also dealing with the encryption issue, how to be able to still detect to still do deep packet inspection even if the traffic is encrypted. Thank you.